Hi, ReactNL. I am James Kyle. I'm an engineer at Facebook. I recently joined the Flow team, which is a static type checker for JavaScript that you should all use. I once helped make Babel a thing. I sometimes maintain a pretty cool project called Lerna. And I also recently been working on a new project called Yarn, which we just open sourced 2 days ago. This is also my first time in Amsterdam, and I have a bit of a confession to make. Amsterdam, I love you. I love the bikes, the canal, the drugs, the waffles, the art, the drugs. Meanwhile, in the US, we're still trying to figure out if we can elect an actual baby for president. What I'm trying to say is, Amsterdam, I love you. You can also follow me on Twitter at @JamesKyle. My personal sense of self-worth comes from GitHub stars and Twitter followers, so please do follow me. Today, I'm going to teach you how to build a compiler. And maybe you're thinking, but I don't want to learn how to build a compiler. Well, too bad. I'm going to teach you, and you're going to deal with it. But before I dive into things, I want to talk a bit about how this talk came to be. I became interested in compilers through Babel, or 6-to-5 as OG people call it. I knew what compilers were and how they generally worked, but I wasn't really able to understand them until the 2 years now I've been working on Babel. It wasn't until I first looked at the 6-to-5 code base that I started to understand how compilers work. I was able to read the actual code of a compiler and understand it. Once Babel grew into a really massive project, just show of hands how many people here use it. Yeah, it's overwhelming. It was sort of hard to not notice how few contributors we were getting. I encouraged people, I gave talks, I explained the code base and these live podcasts, but I quickly learned that people are just fundamentally scared of compilers. It has this image problem of being just totally unapproachable, and something that only someone with a doctorate could understand. I realized that we need to do a better job of teaching people and making compilers more approachable. So I decided I was going to go out and really learn everything there was to know about compilers. I jumped onto Amazon and ordered all of the essential books on compilers, and about 3 weeks later, I discovered why compilers were unapproachable. In the mail came these 3 or 4 different books, each of them 600 pages long, and all of them completely boring. They were 500 pages of the most dull explanations of compilers that ever could have been written. I love compilers, and I was so bored reading them. I couldn't come close to finishing them. The learning problem with compilers is not that they're complicated, it's that we teach that they're complicated. So what I'm going to do today is give you an oversimplified but reasonably accurate overview of what most compilers look like. And then I'm going to try making it more real to everyone here by walking through the code of an actual compiler that I've created. So what even is a compiler? A compiler is simply a tool that transforms source code written in a higher-level language into a generally lower-level target language. But let's go back to the fundamentals to explain why they exist. A computer's CPU executes millions and billions of tiny little operations so tiny that you would never want to write them out manually. In their sort of pure form, they're written as binary. This is known as machine code. It's the code the machine is actually executing. Obviously, There is no way a programmer could understand and be productive writing code like this, so CPU architectures support a mapping of binary operations to an easier read language like this. And this is known as assembly code. It's a super low-level programming language that gets converted into binary machine code by a thing called an assembler. Externally, an assembler looks very similar to a compiler. It's taking one type of code and translating it into a lower-level type of code. However, internally, they are much simpler than compilers. Ignoring any optimizations an assembler might do, they're really just a straight mapping of one syntax to another. However, assembly code is still too low-level to be productive in. So the next layer up is source code. And this is where the vast majority of programmers enter. These are programming languages that you are familiar with and you would actually write large pieces of software in. Source code is different than assembly code. In most cases, it doesn't map directly to machine operations. It's meant as an abstraction to allow humans to understand what is happening and be productive in writing code. As such, an assembler wouldn't be able to translate source code down into machine operations. We need something that can understand a more complicated syntax and transform it very intelligently into optimized lower-level code. And this is where a compiler comes in. Since compilers are doing complicated operations, they have to be broken down into a couple different stages. These stages vary compiler to compiler, but they all fit within three primary groups: parsing, transformation, and code generation. Parsing is taking raw code and turning it into a more abstract representation. Transformation is taking this abstract representation and manipulating it to do whatever the compiler wants it to. Code generation takes the transformed representation of code and then turns it into new code. So like we can go from like this really abstract thing to like a string of actual code that we can use. So parsing gets broken down into a couple different phases. The two biggest ones that you're ever going to see are lexical analysis and syntactic analysis. Lexical analysis takes raw code and splits it apart into these things called tokens. Tokens are an array of tiny little objects that describe an isolated piece of the syntax. They could be numbers or labels or punctuation or operators, whatever. Syntactic analysis takes the tokens and reformats them into a representation that describes each part of the syntax and their relation to one another. This is known as an intermediate representation or abstract syntax tree. An abstract syntax tree, or AST for short, is a deeply nested object that represents code in a way that is both easy to work with and tells us a lot of information. For code, we would represent tokens something like this. We have, you can see the parem, the name, the number, and you can see like the actual values of them. They're just broken apart nice and even. In an abstract syntax tree like this, and you can see we have a program, and inside that program we have a body with a call expression that gets a param with number literal, and so on. The next stage of a compiler is transformation. Again, this just takes the AST from the last step and makes changes to it. It can manipulate the AST in the same language, or it can translate it into an entirely new language. Let's look at how we would transform an AST. You might notice that our AST has elements within it that look very similar. These are those objects with a type property. Each of these are known as an AST node. These nodes have defined properties on them that describe one isolated part of the tree. So we can have a node for a number literal, which is that type and then the value of it. Or a node for a call expression, which has that name and then has room for more nodes within it for params. And when transforming the AST, we can manipulate nodes by adding, removing, replacing properties. We can add new nodes, remove nodes, or leave the existing AST alone and create an entirely new one based on it. And since, for the purposes of this talk, we're going to be targeting a whole new language, we're We're going to mostly focus on like taking the AST and creating a new one that's based on that last AST. In order to navigate through all of these nodes, we need to be able to traverse through them. This traversal process goes through each node in the AST depth first. So for the following AST, we would go from the program and see that it has an array of nodes in the body and go down to call expression and then down to number literal and down and move on to call expression, and we do it through that way. If we were manipulating this AST instead of creating a new AST, we would introduce a lot of different abstractions here, but just visiting each node in the tree is enough. And the reason I use the word visiting is because there's this pattern on how to represent operations on elements of a tree. The basic idea is that we're going to create a visitor object that has methods defined on it that accepts different node types. When we traverse our AST, we're going to call the methods on this visitor whenever we encounter a node of the matching type. In order to make this more useful, we're going to pass in the node and its parent node. The final phase of a compiler is code generation. Sometimes compilers will do things that overlap with transformation. But for the most part, code generation just means we take our AST and stringify the code back out. Code generators work in several different ways. Some compilers will reuse the tokens from earlier. Others will create like a whole new representation so that they can print it out better. But from what I can tell, most will just use that same AST we've created, and that's what we're going to focus on. Effectively, our code generator will know how to print all of the different nodes and node types of the AST, and it's going to like recursively call itself to print all of the nested nodes into like one giant string at the end. You'll see. And that's everything. That is all the major phases of a compiler. Now, that isn't to say every compiler looks exactly what I've described here. Compilers serve many different purposes, and they may need way more steps than I've detailed, like type checking and all sorts of stuff like that. But now you should have like a general high-level sense of what most compilers look like. So you can all build one, right? It's just go. No. Well, when I was thinking of how to create this talk, I knew I wanted to frame things from a more comfortable perspective. But I also wanted to teach in the same way that I learned, by reading actual working code. So when I went to write this talk, I declared that I would write the world's smallest compiler, thinking that would be super easy. I just have a couple of requirements. It has to demonstrate what a real-world compiler would do. It has to do something complicated enough to justify building a compiler. And it has to be a small enough piece of code that it can be explained in a conference talk. Well, turns out that's really difficult. I tried all sorts of things. Like, I spent months on this. And eventually, I just gave up. There was just no way I was going to write a compiler for a talk and make that like work. So it just wasn't a practical idea. Fast forward a bit, and I started learning a bit more about Lisp languages. If you haven't seen them before, just take the code you write and put parentheses like just everywhere, just for no reason, just all over the place. But I played around with a couple different languages, and I discovered how powerful their compilers are. Interested, I started looking into how Lisp languages get compiled. Because their syntax is very different. Just parentheses. And then I realized that Lisp was the perfect syntax for this compiler. It's a super simple syntax to parse, and it's very easy to translate into another language syntax. I played around with the idea, and after only a couple of hours, I had what was a pretty viable candidate for a talk. The entire source is just over 250 lines of actual code. So if you're unfamiliar with Lisp, it looks like this. If that looks weird to you, it's basically just taking the parentheses of code you write and just putting it on the outside. And it's just that in a mathematical expression. So this is what we're going to do. We're going to take a compiler that takes a basic Lisp-like syntax and turn it into a C-like syntax, like JavaScript, which is very related to C. So here it is, the code of our compiler. We're going to start up with the first phase of parsing lexical analysis with a tokenizer. So we're going to take our string of code and turn it into an array of those tokens. We start by accepting an input string of code, and then we're going to set up two things. A current variable for tracking our position in the code like a cursor, and a tokens array for pushing our tokens to. We start by creating a while loop, where we're setting up our current variable to be incremented as much as we want inside the loop. We're going to do this because we're going to want to increment current many times for a single token. Because a token can be any length. It can be just 1, 3, or however many characters it is. And yeah. The first thing we're going to do is check for an open parentheses. This will be used later for call expressions. But for now, we only care about this first character. So we create it, push it, and move on. Yep, that. Next, we're going to go and check for a closing parentheses and do the exact same thing as before. Moving on, we're now going to check for white space. This is actually a bit interesting because we care that white space exists because it separates characters, but it's not actually important for us to store as a token. We would just throw it out later because it's just meaningless. So here we're going to test for existence, and if it does exist, we're just going to move on. The next type of token is a number. This is different than what we've seen before because a number could be many characters, and we want to capture all of the characters in one sequence. So to start off, we start off when we encounter the first number in a sequence. We create a value string that we're going to push characters to, and then we loop through each character in the sequence until we encounter a character that is not a number, pushing each character that is a number to our value and incrementing current as we go. After that, we push the number token to our tokens array and move on. The last type of token is a name token. This is a sequence of letters instead of numbers that are the names of our functions. And we're going to do the same thing of looping through letters, pushing a token, and moving on. Finally, if we have not matched a character by now, we're just going to freak out and just throw a type error because we don't know how to parse that. So at the end of the tokenizer, we just return the tokens array. Now for the parser. So for our parser, we're going to take our array of tokens and turn it into an AST. So we define the parser function, which accepts our array of tokens. We, again, track a current variable to use as a cursor, this time for the tokens, not the characters. And this time, we're going to use recursion instead of that while loop from before. So we define a walk function. Inside the walk function, we're going to start by grabbing the current token. We're going to split off each type of token into a different code path, starting with number tokens, where when we encounter the type, we just create a node out of it and move on. Move on. And next, we're going to look for call expressions. So here, we start off when we encounter an open parentheses. We increment current to skip the parentheses, since we're not going to put that anywhere in our AST. We create an empty node with the type call expression. And we're going to set the name as the current token's value, since the next token after parentheses is the name of this function. We increment current again to skip the name token. And now we want to loop through each token that will be the params of our call expression until we encounter a closing parentheses. So we create a while loop, and we continue until we create a token with a type of paren and a value of a closing parentheses. Now this is where the recursion comes in. Instead of trying to parse a potentially infinite nested set of nodes, we're going to rely on recursion to resolve everything for us. So to explain this, let's look at our Lisp code. You can see that the parameters of the add are a number and a nested call expression that includes its own numbers. You'll notice that our tokens array, we have multiple closing parentheses. We're going to rely on our nested walk function to increment that current variable from before past the nested call expression so that we can just see the final one. So back to the code, we'll call our walk function, which will return a node, and we'll push that to the params of our node, and we're going to move on. And finally, we're just going to return that node. Again, if we haven't recognized the token type, we're going to throw a syntax error. Now, finally, we're going to create our AST, which the root of which will be a program node. And then we're going to kickstart our walk function, pushing nodes to program.body. The reason that we're doing this inside a loop is because our program can have call expressions one after the other instead of being nested. And then finally, at the end of the parser, we will return our AST. Next up, the traverser. So now that we have our AST, we want to be able to visit different nodes with a visitor. We need to be able to call methods on the visitor whenever we encounter a node with a matching type. We're going to define a traverser function, which accepts an AST and a visitor. And inside, we're going to define two functions. Traverse array, which will allow us to iterate over an array and call the traverse node method, which is our next function, which will accept a node and its parent node so that we can pass those on to our visitor methods. First, we're going to test for the existence of a method with the matching type. And if it does exist, we're going to call it with our node and parent. Next, we're going to split things up by the current node type. We'll start at the top level program. Since program nodes have a property named body that is an array of nodes, we will call traverse array and traverse down into them. Remember that traverse array will in turn call traverse node, so we're causing the tree to be recursed. Next up, we'll do the call expressions, and we're going to do the same thing of traversing their parameters. And finally, in the case of number literals, we don't have any child nodes to visit, so we'll just break. And again, if we haven't recognized the node type, we'll throw an error. Finally, we will kickstart the entire process off by calling traverse node with our AST. Next up, the transformer. Our transformer is going to take the AST that we have built and pass it to our traverser function with a visitor, and we will create a new AST. This AST is designed for JavaScript. It's actually the Babel AST. Not that you can tell that much. So we have our transformer function, which will accept the Lisp AST. We'll create a new AST, which, like our previous AST, will have a program node. Next up, I'm going to cheat a little bit and create a little bit of a hack and hand wave. We're going to use a property named context on our parent nodes so that we can keep our traverser flat. Inside the methods of the visitor, we're going to keep pushing nodes to the parent's context. Normally, you'd have a bit of a better abstraction than this, but this keeps things a little bit simpler. We'll start by calling the traverser function with our AST and a visitor. The first visitor accepts number literals. We're just going to push to that parent's context a new node with a number literal and value. And then call expressions. We're going to create an expression with the node name. We're going to add the arguments to the node's context. And then if the parent type is a call expression or is not a call expression, we're going to wrap it with an expression statement because top-level expressions in JavaScript are actually statements. And then we're just going to push our possibly wrapped call expression to the parent node's context and be done. Finally, let's move on to our last phase, the code generator. Our code generator is going to recursively call itself in order to print each node into the tree into one giant string. So we'll break things down by node type. If we have a program node, we'll map through each node in the body and run them through the code generator, which will join them with a new line. For expression statements, we're going to call the code generator in the next expression, and then we're just going to add a semicolon because we like to code the correct way. For call expressions, we're going to print the callee, add an open parentheses. We'll map through each node in the arguments array, run them through the code generator, join them with a comma, and then we'll add the closing parentheses. For identifier, we're just going to return the node's name. And for number literals, we're just going to return the node's value. Finally, if we have not recognized the node, we're going to throw an error. Finally, we will create our compile function. Here, we're going to link together every part of the pipeline and turn it into one solid thing. We'll take the input and pass it into the tokenizer and create our tokens. We'll pass the tokens into the parser and create our AST. We'll pass the AST in the transformer and create a new AST. We'll pass the new AST into the code generator and generate the output, and then just return the output, and we're done. That's it. That is all the code of our compiler. But let me prove that works to you. So here's our tokenizer with a string of input. There are the tokens. Hooray. Parser, take those tokens and turn it into an AST. Transformer, take that AST and turn it into a new AST. Code generator, take that new AST and turn it into a string. And then all together, we'll take the input all the way to the end, and we will generate our program. And that's my talk. Follow me on Twitter. Thank you all. Goodbye. Hello, ReactNL. My name is James Kyle. I'm an engineer at Facebook, Flow, Babel, Lerna, Yarn, Amsterdam, bikes, canals, drugs, waffles, art, drugs, baby president. I love you. Please follow me on Twitter. I'm going to cry. OK. So I am also here today to talk to you about Yarn. If you have not seen it already, just earlier this week, we open sourced a new project called Yarn. Yarn is a new package manager. It is a replacement client for NPM and Bower. It is ultra fast. It caches every package it downloads so that it never needs to again. It also parallelizes operations to maximize resource utilization. So install times are faster than ever. Also, if you have any native modules that need to be compiled, it does that in parallel. It also caches the results. It does all sorts of things to make sure that the subsequent installs are as fast as humanly possible, or computerly possible. It's much more secure. It uses checksums to verify the integrity of every installed package before its code is executed. It also does not store credentials or tokens or anything like that. You do have to authenticate again when you publish so that some hacker who just walks up to your computer can't publish. It's super reliable. It uses a detailed but concise block file format. It uses a deterministic algorithm for installs. And Yarn is able to guarantee that an install that worked on one system will work exactly the same way on another system. That being your coworkers or your CI or whatever. You get the same exact thing every single time, and that's just better. It is. Yarn also has tons of other features, which brings the JavaScript ecosystem up to date with a lot of other modern packagers out there. Cargo being sort of like the gold standard. That's the Rust one, by the way. So we have offline mode, so that because we place all the packages in a cache, it can just install from that cache again in the future. Again, it's deterministic. It works with the existing registries that you already use, npm and bower. It can solve from Git and all that. It's resilient against network failure, so that if requests fail, it can retry them and not like give up entirely and dump 10,000 lines of errors. It can resolve things to be flat. If you're familiar with Bower, you can resolve things down to a single dependency, which is useful for things like React, where you don't want multiple copies ever, because that just doesn't work. And yeah, it's also more performant because it queues things up and sort of makes sure that everything, it's always using as much of your computer CPU as possible. So what are we waiting for? Let's see it in action. If I can, this is going to be so much fun. Here we go. So I have cleared, this is the React Native repo. If anyone's ever run an install in there, it's very long. And I have completely nuked the node modules directory. And for both yarn is going to be on the left and npm on the right. I have to type over here now. I'm going to clear this again. So here we go. I'm going to erase here. I'll dance. Done. Meanwhile, they say it's crazy to run an install and to talk. Meanwhile, we have npm, which is still resolving metadata. This will go on for several minutes. Yeah, so this was just released. I hope that you all use it and report bugs and help contribute. I don't know what that did. Yeah, it's meant to work with the way you're already installing things, just short little migrations. The commands are slightly different, but yeah. I'm not going to keep talking until that's done, because no thank you. Yeah. So that is yarn. That's all I have.